consecutive walks. This time s equals 0. There's no stay in the same place, but it's just one type of right walk and one type of left step. So, for example, these are the 5 possible dig paths with 6 steps. 1, 2, 3, 4, 5, 6. And if you do the same thing, substitute these values into our general formula for p of x, this one here, put s equals 0, and L and R both equal to 1, you get 1 minus the equation 1 minus 4x squared over 2x squared. Which generates this sequence here. This sequence here, or these numbers, 1, 1, 2, 5, 14, 42, are well known to people in combinatorics as the Catalan numbers, probably have even more applications than the Fibonacci numbers. And the thing to notice is that all dig paths, unlike Motzkin paths, have an even number of steps. So we've got a bit of redundancy here. I mean, we've got this series here only has even terms. So we could instead just talk about dig paths with 2n steps and then have a slightly simpler generating function, which is actually what we'll do a bit later. Okay, so the final theorem I want to mention has the fancy name, the fundamental theorem of Riordan arrays, FTRA for short. And it turns out this is actually very useful. It's also simple to prove using matrix multiplication. So basically what we have is this. We have our Riordan array, this is the matrix, and we multiply it by a column vector, which are the components of the generating function, and we get, if this is true, so if this relation is true, so the matrix multiplied by this vector gives us another infinite vector, then it's also true that the generating function corresponding to this sequence h is equal to p times g of q. So we'll see why this is useful very shortly. So we're going to apply this theorem to finding the average number of what are called hills in a dig path with 2n steps. So first of all, what do we mean by a hill? Well, a hill in a dig path is an up step immediately followed by a down step, and the up step has to start on the x-axis. So going back to this picture here, this is a hill, and this is a hill. Okay, it's an up step followed by a down step, and the up step always starts on the x-axis. So this is a hill, this is a hill, and these are 3 hills here. So the total number of hills for all dig paths of length 6 is 5. And we also notice that the number of dig paths of length 6 is the same number 5. So the question might be, well, is that always true? Obviously it's not going to be true for n equals 0, because we sort of tend to count n equals 0 as having one path, but obviously there's no hills in that. But for n greater than 0, is it always true that the number of hills, the total number of hills for all possible dig paths of 2n, length 2n, is equal to the number of dig paths of length 2n? So that's what we can prove using this fundamental theorem of Riordan arrays. So we define our matrix P of Q, PQ. We haven't proved it's a Riordan array. I'm just writing it as a Riordan array format in the hope that it will turn out to be a Riordan array. So this is just a matrix entry NQ. So this matrix entry NQ, we're saying, is the number of dig paths with 2n steps that have precisely k hills. So if this is a Riordan array, then the first column must be the coefficients of the generating function for p of x. So the first column corresponds to 0 hills. So that means that px must be the generating function for the number of dig paths with no hills. So in other words, if you look at the nth row, that gives you the number of dig paths which contain 2n steps and have 0 hills. So for example, in this case, n equals 3, because we've got 2n is 6. In this case, the number of dig paths with no hills would be 2 in this case. So P3 would be 2. Now the generating function for the number of dig paths with 1 hill, it turns out, is p times x times p. This takes a little bit of thinking about. But basically the idea is that you say, well, if I'm going to have one hill, that hill is going to be surrounded by two dig paths with no hills. So if we take this hill here, then to the left of it is a dig path with no hills, and then to the right of it there's a sort of dig path with no hills. It's a sort of zero length dig path with no hills. And we do the same thing in general. So the generating function of the number of dig paths with k hills, we do the same thing. It's p times x times p times x, k times. So overall we end up with p. So this is going to be the generating function for the kth column. That's going to be p times xp to the k, which means that according to our formula for going back, if you remember what, right back to the beginning, if you remember what our Riordan array actually means, it's the kth column is p times q to the k. So it means that in this case, we've already found what q is. Q has to be x times p. So it turns out that dig paths are related, as I mentioned, to the Catalan numbers. So c of x is the generating function for, well, okay, we let c of x be the generating function such that cn is the total number of dig paths with 2n steps. It turns out that cn are the Catalan numbers which have this generating function. Now what we do is say we're going to decompose this generating function for all possible dig paths with 2n into the different cases. So the case with 0 hills we know is the generation function p. We've just argued that the case for 1 hill is x times p, and so on. But this we can just rewrite as a geometric series. Well, sorry, it is a geometric series. We sum the terms and we get this as an expression for c. So in principle, from this we could actually work out what p is. Because we know what c is. In fact, it turns out we don't need to. So the last step is to count the hills. So we let h be the generating function we're after. This is the generating function such that the terms in the coefficients, hn, are the total number of hills present in all dig paths. So we sum up all dig paths of length 2n. And then to get this h, what we basically do is multiply this Riordan array by a column vector which gives us the number of hills in each row. In each column. So this g, so basically what we're going to do is use this formula here. This is our Riordan array. We're going to multiply it by a column vector g and end up with the number of hills in this column vector h. So g is just the counting numbers. So we've got 0 hills, 1 hill, 2 hills. This is a matrix where, remember, the nth row gives us the number of dig paths, the number of dig paths with each possible value of k, each possible number of hills. So when we multiply a row by this column vector, we'll end up with a total number of hills of a particular value of n, which is precisely what we want. Okay, so this is h of n. Now, if this is true from the fundamental theorem of Riordan arrays, then we have this result here, which gives us the generating function for h. So we basically know what all of these things are now. We just plug them in. So g is x over 1 minus x squared. So plug q into that, we get q over 1 minus q squared. And q, we know is x times p. So we can plug that in. So replace q by x times p, we get x times p squared over 1 minus xp squared. Now fortunately we already know what this is, because on the previous slide notice that we have c, the generating function of the Catalan numbers, or the generating function for the number of dig paths is p over 1 minus xp. So this is just p over 1 minus xp all squared. So we end up with x times c squared. And it turns out that the generating function for the Catalan numbers actually satisfies this quadratic equation, the solution of which is, well, what you expect for a quadratic equation. So we can simplify this. Xc squared is actually just equal to cx minus 1. So what do we have? Well, the generating function for the number of hills is the same as the generating function for the number of dig paths, which means except when well, the coefficient of x to the 0 is wrong, okay, but otherwise the higher coefficients when n is not 0, then this is true. So basically we have that the number of hills is equal to the total number of hills is equal to the total number of dig paths, which is what we're trying to show. So the average number of hills is 1. Okay, so that's about all I have to say. So what I was talking about today, this sort of laid the foundations really for the concept of Riordan arrays. These are the people who actually named the Riordan arrays. This talk was sort of based heavily on this paper, and also this is an article which the last bit about the counting the hills came from. So that's the end of the talk. Yes.
So you mentioned a way to get like a matrix from a pair P and Q, right?
Yes.
And you said that the unified group operation is just like multiply matrices.
Yes.
But is that like a one-to-one correspondence? So in other words, if you have a matrix which is comes from some pair PQ.
Yes.
Is this pair unique?
Oh, so what you're saying is that
In your definition of the
okay. So you're saying that if you have a matrix, is there only one pair of P and Q that matrix could come from?
Exactly.
I imagine. Oh, I'm not. Okay, if you have a matrix which is a Riordan array, then it must have an A sequence. And if it has an A sequence, then